Welcome back to section 1.7. Now, we're going to be talking about transformations of functions. And these transformations work for our algebraic functions we're talking about now and also our trigonometric functions. So we're going to be starting off with rigid transformations, where the basic shape of the graph is unchanged. So we have what are called vertical and horizontal shifts. So you can see when we're adding c after the function, or subtracting c, that's going to be a vertical shift when that constant is after the function, not in parentheses. That's our horizontal or vertical shifts, excuse me. Now, when it's inside the function, that's going to be our horizontal shift. We're used to seeing it like this, that y equals the quantity of x minus h plus k. H is our shift left and right. And then k, the number outside, is our shift up and down. And that kind of relates to what we had seen in Algebra 2. So what you want to do is you want to graph the anchor points and then apply the shifts. It doesn't matter if you do horizontal shift or vertical shift first. You just want to make sure you do both. So for problem number 1, we're just going to identify the shift. So another way to write this is that f of x equals, I'm going to write x squared plus 1. There's no grouping symbols, so really there's no h, so h is 0 and k is 1. So what we're doing is we're going to be shifting up 1. For number 2, h is 0. There's nothing in the grouping symbols, and k is negative 4. So we're going to be shifting down 4. For number 3, x plus 4 is in parentheses. So what we want to think about it setting x plus 4 equal to 0, x equals negative 4, and also it's y equals x minus h. So we're subtracting a negative 4. So that's why h is the negative 4. We want to change the sign inside the grouping symbols, and k is 0. So we're going to the left 4 for that one. Number 4, h, take the opposite of that negative 2, so it's going to be 2, and k is negative 3. So we're shifting to the right 2 and down 3. There's our transformations. Now, when I talk about the parent functions, I will give you a set of graphs for these parent functions and as well as the anchor points, and I'll upload that onto Canvas so you have access to it. But our parent functions, our anchor points, are going to be the same for this case, quadratic. Now, if we look, h is 0. There's nothing in parentheses, and k is 2. Now, our anchor points, 0, 0, 1, 1, 2, 4, 3, 9. Same with the negatives. So what we're going to do is we're going to take each one of those points and we're going to shift them up 2. And we can draw our graph through those points. So that's using the parent function and anchor points, and we're shifting everything up 2. That's our graph. Now, g of x is the absolute value of x minus 1. So the absolute value of x, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so forth, looks like that v. So now, h, because we have a value in parentheses, is a positive 1, and k is 0. So what we're going to be doing is we're going to the right 1. So take each point and go to the right 1. And here is our graph. We just literally shifted everything over to the right 1. The shape stays the same. Number 7, the square root function. So our anchor points for a square root function are 0, 0, 1, 1, 4, 2, and 9, 3. Now, H is 0. There's nothing in the grouping symbols, and K is -3. So we're taking everything and going down 3. So I'm going to take each point and go down 3, down 3, down 3, and down 3. And then we're going to draw our graph through those points. And there is our new function that shifted down 3. For number 8, the quantity of x plus 2 squared minus 1. So our parent function x squared 0, 0, 1, 1, 2, 4, and for the opposite, 3, 9, -3, 9. Now, h in parentheses is a -2. K is a -1. So we're going to go to the left 2 and down 1. So I'm going to take each point and go to left 2, down 1. 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 And there is our graph. And that's the importance of knowing what the parent functions are and what those anchor points are. Like I said, I will provide a sheet with all of those anchor points and the parent functions for you to have access to make this even easier. You'll start memorizing them the more you use them. Now, we have another transformation called a reflection. We could have an x-axis reflection or a y-axis reflection. We're most familiar with the x-axis reflection. That's where the negative is on the outside of the function. So it's -1 times whatever f of x is. Now, a y-axis reflection is when the negative is inside the function. You see how it's inside the parentheses? That's a y-axis reflection. So we're going to look to see what kind of reflection we have, or which one of these, is a reflection along the x-axis. When it's an x-axis reflection, the negative is on the outside. So we know that B is gone, and because of the negative exponent, C is gone. Now, we're between A and D. Now, they're very similar, except A is just a -1, and D is a -2. There's another transformation going on there that we'll talk about later. So our only answer is A. That has just an x-axis reflection. D also has an x-axis reflection, but it has more going on to it. Now we're going to sketch the parent function and then the shifted functions. So the parent function for these absolute values is this. That's our parent function. Now, I'm not going to draw the whole thing just because I don't want to confuse ourselves. The negative is on the outside, so there is an x-axis reflection. Now to do that, we're going to multiply each output by -1. So 0 times -1 is 0. 1 times -1 is -1. 2 times -1 is -2. 3 times -1, -3. -4, -5. Same thing over here. We're really just taking those anchor points and flipping them along the x-axis. And here is our new graph. For f of x equals -x. The negative is on the inside, so it's a y-axis reflection. Now, plotting my anchor points once again, my parent function points. We have a y-axis reflection. So you're multiplying now the x's by -1. So 1 times -1 is -1. 2 times -1 is -2. 3 times -1 is -3. 4 times -1, same thing. -5 times -1 is 5. Times -1 is 4. Times -1 is 3. When we reflected along that y-axis, nothing happened. It's the same as our parent function. And that's because this is symmetric along that y-axis. We had y-axis symmetry. And because of that y-axis symmetry, it didn't change our graph. It's the same graph for that one. I can't spell graph. Now for number 12. For y equals x cubed, plotting our anchor points for our parent function. Now, it has x-axis reflection. For x-axis reflection, you multiply the y by -1. 8 times -1 is -8. 1 times -1 is -1. 0 times -1 is 0. 1 times -1 is -1. -8 times -1 is 8. So this is our graph. That's that x-axis reflection. We reflected it along the x-axis. We flip all the points from the bottom to the top and the top to the bottom. Let's see a couple more examples of this. For number 13, the opposite, negative x cubed. Now this has y-axis reflection because the negative is on the inside. We'll once again plot our anchor points. And now we'll multiply the x values by -1. So 2 times -1 is -2. 1 times -1 is -1. 0 times -1 is 0. -1 times -1 is 1. -2 times -1 is 2. You can see what we did is we switched any point from the left, we moved it to the right, and vice versa. That's our graph. The negative x squared, the negative's on the outside, so it's x-axis reflection. So for that x-axis reflection, what we have here is our anchor points for our quadratic. They're the same each time. Now we're going to multiply the outputs, the y's, by -1. 9 times -1, -9. 4 times -1 is -4. 1 times -1, -1. 0, -1, -4, -9. And there's our graph with the x-axis reflection. And then -1 times x cubed is x-axis reflection. Get you my anchor points first. We multiply by the y values by -1. So we're at 8, 8. Went a little too high. We're at 8, so we're at -8, -1, 0, 1, and then up to 8. Interestingly enough, for 15 and 13, it's the same graph, even though one had x-axis reflection, the other one had y-axis reflection. And the reason is that graph had origin symmetry. And origin symmetry is x and y-axis. Now for number 16, we're going to graph f of x equals square root of -x. So the square root of x, our parent function, 0, 0, 1, 1, 4, 2, 9, 3. That's our parent function now. Because of where the negative is, that has y-axis reflection. So we're at 0, 0. We're multiplying the x values by -1. So -1. 4 times -1 is -4. 9 times -1 is -9. And then here is our graph. There's that y-axis reflection, excuse me. So our domain is from -infinity up to 1 with a bracket, and our range, remember, we're going from smaller to larger. It starts at 0 and goes up towards +infinity. We'll also be talking about non-rigid transformations, and these are our stretches. So when our constant's on the outside, that's a vertical stretch. So when that constant is greater than 1, it's going to be a vertical stretch. It's going to make our graph skinnier. When that constant on the outside is between 0 and 1, it's going to be a vertical shrink. It's going to be a wider graph. So what you would do is you'd multiply each y value by c. Now, when the constant is on the inside of the function, that's going to be a horizontal shrink or stretch. Now, when it's greater than 1, this is a little bit different than the other one. It's going to be a shrink. The values of x move closer together. When c is between 0 and 1, it's going to be a horizontal stretch. The x values move further away. So what you would do is you'd multiply actually each x value by 1 over c. The horizontal ones are much trickier. Now there's an order to applying these transformations. You want to do the stretch and shrink first, whether it's horizontal shrink stretch or vertical shrink stretch, you do that first. Then the reflection, and after all of that, then you can shift up, down, left, and right. So that make sure you do that in that order. Don't do any shifting until you do all your stretches, shrinks, and reflections. We're going to stop there, and we're going to come back and do more examples in part 2.